Hello, I'm Michelle Crummell, and in this video we're going to take a look at how we can use Riemann and trapezoidal sums to approximate the area under a curve. And when we say area under a curve, what we really mean is the area in between the curve and the x-axis, possibly on some interval. So for example, in this problem, if we are referring to the area under the curve between x equals 0 and x equals 7, then we are referring to this shaded area. I'm going to stop when I get to x equals 7. So it's not everything under the parabola, but just this shaded region right here. Instead of counting squares, we are going to create rectangles in our region and then find the area of each rectangle and add them together. So we're going to do this in a systematic way. We're going to start by making rectangles that have a width of 2. And let's suppose the interval we're working on is the interval from 1 to 7. So I'm going to ignore the parts of the graph that are outside of that interval. We're just going to look at 1 to 7. So I'm going to go ahead and highlight the area that I'm referring to. So it's just this area between, I went a little too far there, between x equals 1 and x equals 7. That's the area that we are trying to approximate here, and we are going to do so by creating some rectangles. So our first rectangle, it has a width of 2. So it's going to come up like so. Now, how tall should I make this rectangle? We have to have a way to decide how tall this rectangle is going to be. So we are going to place the left edge of each rectangle on the curve. So basically, the left side of the rectangle, I went a little too far there. The left side of the rectangle, we're going to follow up right until we hit the curve. And that point there is going to determine the height of the rectangle. So it's that left edge of the rectangle, wherever it intersects the curve, is going to determine the height of our rectangle. Now I'm going to make another rectangle, also of width 2, here. And I'm going to follow the left side of the rectangle up until I hit the curve. And that's going to determine the height of the next rectangle. So we can see that this is imperfect. Part of our rectangle extends outside of the curve, so it's not capturing, well, it is capturing more than all of the area of the shaded part. And in my first rectangle, I have failed to capture all of the area that I needed to between 1 and 3. So it's not perfect, but it's giving us a rough estimate. And then we'll do this one more time with one more rectangle to take us from 5 to 7. We're going to follow the left edge up until we hit the curve, and that will determine the height of the rectangle. So again, we see this last rectangle is really not doing a great job of capturing the correct amount of area there. But it's simple enough to calculate the area of a rectangle. We know that the width is 2, and then the height is just this function value at f of 1 right here. So the area of the rectangle is 2 times f of 1. The next rectangle also has a width here of 2, and the height is f of 3. So the area here, 2 times f of 3. And then the third rectangle, the height is f of 5. The width here is 2, so the area equals 2 times f of 5. And we can compute f of 1, f of 3, f of 5, because we have the equation here for f of x. So I've already done that for us, f of 1, f of 3, f of 5. And so now we can approximate the area as 2 times f of 1 plus 2 times f of 3 plus 2 times f of 5. And that turns out to be 42.667. So it's not the exact area, but it gives us a rough estimate of the area. This technique that we just used is called a left Riemann sum. It's called a left Riemann sum because we are using the left endpoint of each of these subintervals. We've got an interval that goes from 1 to 3, from 3 to 5, and from 5 to 7. So we're using the left endpoint of each interval to determine the height of the rectangle. So it is a left Riemann sum. Let's try this again, but instead of using rectangles of width 2, we're going to use rectangles of width 1. We're still working on the interval from 1 to 7. So going to use the left endpoint. So my intervals now are going to be 1 to 2, 2 to 3, 3 to 4, and so on until I get to 7. So x equals 1 is going to be where my left end point is for my interval. We're going to follow that up till we hit the curve, and that's going to determine the height of our rectangle here. And then f of 2, left side goes up until we intersect the curve. That determines the height of that rectangle, and so on. So you can see that some rectangles extend outside of the curve, and some fall below the curve. And here, if we want to calculate the area of each rectangle, they each have a width of 1, and their heights are f of 1, f of 2, f of 3, f of 4, and f of 5. The last rectangle did I not draw that right? I did not draw that right. Let me fix that. Right, so for f of 5, we're going across like so, and then f of 7. Oh, I think I just missed one of my rectangles there. Okay, f of 5, f of 6, and then notice that we don't have an f of 7 because our last rectangle, the height is determined by the left endpoint of the interval, not the right endpoint of the interval, so we don't actually use the x equals 7. Okay, now our heights are going to be 1 times f of 1, or I'm sorry, the areas, 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3, and so on, giving us an estimated area of 41.667. If we try this again and let the width of the interval be 0.5 instead of 1, we're going to have twice as many rectangles as we did when the width was 1. And you can see, hopefully, that we're going to get a better approximation, right? In terms of how good is the approximation, we want to be looking at, and let me do some shading here. We want to be looking at how much area did we fail to capture, right? We failed to capture that right there. And then how much excess area did we capture? So this is excess area. And if we have a surplus, right, we're capturing more area than we should have, then that means that our estimation is an overestimate or an over approximation, which is going to happen in this case. If you compare the size of the deficit to the size of the surplus, then we have extra area left over. So we're going to get an overestimate here. So this left Riemann sum is overestimating the actual area. We say under the curve, but again, it means between the curve and the x-axis. So to visually just think about the amount of excess area that we have overall here and compare that to what we have here. Here we do have, we're missing some area here, but then we also have some extra area that we're capturing here. But if we look at the overall, I think we still have a surplus there, right? The overall surplus of area we have here is not as much as what it's going to be here. So things are getting better as we make the width of the rectangle smaller. Now I want you to imagine making it even smaller. What if we were to make it as small as you can possibly imagine? Well, the little gaps in between the rectangle and the curve are going to be very tiny, and so we're going to get a pretty good approximation. When we are using this technique, a left Riemann sum, to approximate the area under the curve, what is the effect of reducing the width of the rectangle then? It's going to give us a more accurate approximation. We'll get a more accurate approximation. When does a left Riemann sum give an underestimate? So it's giving us an underestimate, like here and here. What's different about that, thinking about the function, than where we get an overestimate over here? How's the behavior of the function different? Well, on the left side of the graph here, the curve is increasing. And if the curve is increasing, and you use a left Riemann sum, you're always going to get an underestimate. It doesn't even really matter if you're increasing at a decreasing rate, if you're increasing at an increasing rate, or if you're increasing at a constant rate. You're still, if you're using a left Riemann sum, your rectangles are going to fall short of capturing the full amount of the area. The actual amount of the area that you're trying to capture would be here, right? So we didn't quite get it all. So as long as your function is increasing, whether it's concave up, concave down, or linear, then a left Riemann sum for an increasing function is going to give you an underestimate. And the opposite is true if the function is decreasing. If the function is decreasing, then the left Riemann sum is going to give you an overestimate. Now let's switch up our technique here slightly. Instead of using a left Riemann sum, we're going to find a right Riemann sum. And the difference is when you look at your subinterval, right, our first rectangle, it's between x equals 1 and x equals 3. Instead of using the left endpoint of the subinterval, you're going to use the right endpoint to determine the height of the rectangle. So you go to the right endpoint of your first subinterval, you follow that up until you hit the curve, and that's going to determine the height of that first rectangle. So there's that one. And then we have an interval from 3 to 5. You go to the 5 on the right side of the interval, follow it up until you hit the curve, and that determines the height for that rectangle. So this time, instead of our heights being f of 1, f of 3, f of 5, now they're f of 3, f of 5, and f of 7. We don't use the left edge of the first subinterval. We're not using that value. So the area is now 2 times f of 3, 2 times f of 5, and then 2 times f of 7. And if we calculate that, again, we have the equation, so we can substitute in the 3, the 5, the 7 to get these values here. And then we find the total amount of area from our rectangles, and that is giving us an approximation of 34.667. Now visually we can see that this is an underestimate. We have some extra area here, but we are missing a whole lot of area here and here. Okay, so overall we have an underestimate. This value here is too low. It's not the actual area, it's too low. And the other estimates that we had were a little too high. So the actual area is somewhere in between. If we use a rectangle of width 1 instead of width 2, you can see that we do a better job. Still not great, but we have less error in our approximation. Right? It's a little bit more accurate. So here our heights are going to be f of 2, f of 3, f of 4, f of 5, f of 6, f of 7. And then we multiply each of those heights by the width of the rectangle, which is 1 in each of these cases. And then we add up the areas and we get an approximation of 37.667. Still an under approximation. Visually, I can see that. If we use a smaller width to determine the width of each rectangle, then we're going to do a better job of approximating the area under this curve. So again, I want you to imagine, to get the best possible approximation, how wide would you want each rectangle to be? So the wider they are, the less accurate they're going to predict the area under the curve. So if we want the best possible approximation, then we want the width of each of these rectangles to be infinitesimally small. I don't know how to say that word. Very, 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 very tiny. Now there's a trade-off, right? If you make these subintervals or the width of the rectangles very tiny, then you have many, many, many rectangles, and it's a much more tedious calculation if you are finding the area of each individual rectangle and then adding them together. But luckily, we have a mathematical tool that is going to allow us to let the width of the rectangle approach a number so small that the width is going to be almost 0. And that mathematical tool, of course, is limits. So our approximation here, 38.917. Okay, when using a right Riemann sum, what is the effect of reducing the width of the rectangles? We're going to get a more accurate approximation. When does the right Riemann sum give an underestimate? So this time, you'll notice that we have an underestimate on this part of the curve here. That's where we have an underestimate, and that is where the function is decreasing. So it's the opposite of what it was when we used a left Riemann sum. For the right Riemann sum, if your function is decreasing, you're going to get an underestimate. If your function is increasing, you're going to get an overestimate. So instead of trying to memorize that, because it's easy to mix them up, I always just draw a quick sketch if I need to know, because again, it doesn't matter if you are increasing concave down, concave up, or straight. If you know that you're using a right Riemann sum and your function is increasing, no matter which of these ways it's increasing, a right Riemann sum, if this is the right edge of the height of the rectangle, you have to draw your rectangle out that way, going out that way. And so you can see that we are capturing more than the area under the curve. We're getting too much area, so it's an overestimate. So our best approximation using the left Riemann sum, 40.917. The best approximation when using the right Riemann sum, 38.917. And of course, we could get better approximations if we made the width of each rectangle smaller. So the actual answer is going to be somewhere in between, because I know the approximation on the left is an over approximation, and I know the one on the right is an under approximation. So the real area, the true area, is going to fall somewhere in between those two values. Let's change our technique up again. This time we are not going to use the left endpoint of the interval or the right endpoint of the interval to determine the height of the rectangle. We're actually going to use the middle of the interval, so the midpoint of the interval. And that's going to determine the height of the rectangle. So again, if we want the area from 1 to 7, and we are going to use a width of 2, then that gives me 3 subintervals from 1 to 3, 3 to 5, and 5 to 7. And instead of using the left endpoint or the right endpoint of that first interval that goes from 1 to 3, I'm going to go to the middle. So the middle would be when x equals 2 here. And I'm going to follow that up until I hit the function. And that's going to be the height of the rectangle. So it's going to look like that. Our next interval goes from 3 to 5. We're going to go to the middle, which is 4, follow it up until we hit the curve, and that will determine the height of that rectangle. And then the last interval goes from 5 to 7, so we'll go to the middle, which is 6, follow it up until we hit the curve, and that's the height of that rectangle. So the nice thing about the midpoint Riemann sum is that each one of these rectangles has a little bit of surplus area and a little bit of a deficit. They're kind of balancing each other out, right? Not perfectly, but let's shade this a little bit. So we've got here some extra area, and then here where we're missing some area. So they're not exactly the same amount, but they're sort of, reducing the overall error there, and we're getting a pretty good approximation. And the same thing is going to happen with the next. We've got extra area here, we're missing some area here, and we're missing some area here, and we have some extra area here. Overall, kind of balancing each other out. Not perfectly still, but to find the area of the rectangles, now we are going to use the width of each interval, which is 2, and then the height is determined by that midpoint value, so it's f of 2 this time. The interval, that subinterval, goes from 1 to 3, but the height is determined by f of 2. And then this one by f of 4, and this one by f of 6. So our area this time is going to be 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6, which gives us an estimate of 40.667. So I'm thinking that's pretty close to the real answer, although it still doesn't seem like it's the exact answer just visually looking at the areas. If we make these intervals smaller, meaning the width smaller, then we should be able to do a slightly better job. Let's take a look at that. So here's a midpoint Riemann sum. The width of each rectangle is 1. And again, with each subinterval, we have a little bit of extra area and then a little bit of deficit there. So they're balancing each other out pretty well. And we're getting an approximation of 40.167. If we use a width of 0.5, now we're getting an estimate of 40.042. And it's getting better and better and better. So we could continue along this manner, making the width smaller and smaller as we go until we start getting a number that doesn't seem to be changing for several decimal places, and then we're, pretty close to the real answer. Now with a midpoint Riemann sum, let me also point out, it's hard to tell if overall you have an underestimate or an overestimate. It's definitely not as clear as it is with the left Riemann sum or the right Riemann sum. And the final type of approximation we're going to look at is called a trapezoidal sum. So this one doesn't involve rectangles. We talked about the left Riemann sum, the right Riemann sum, the midpoint Riemann sum, which all rely on rectangles. For this last technique, we're going to create trapezoids instead. So let's again approximate the area on the interval from 1 to 7. We're going to start out with each subinterval having a width of 2. So we'll go from 1 to 3, 3 to 5, 5 to 7. But I'm not going to draw rectangles here. I'm going to draw trapezoids. And the way I'm going to do that is I'm going to take the left endpoint of the interval, follow it up until I hit the curve, take the right endpoint of the subinterval, follow it up until I hit the curve, and then connect those 2 points to create a trapezoid. Now, that might not be what you're used to seeing trapezoids look like, right? Normally when you first learn about trapezoids, you've got parallel bases like so, and then you've got the other sides connected that are not parallel. Well, we certainly can call that a trapezoid, but in our case, our trapezoid is more like one of these kinds of trapezoids where you've got a 90-degree angle formed on one side and then not on the other like that. So that's the trapezoid that we have, and then we're just kind of rotating it 90 degrees, so it's sitting on its side, right? So ours is oriented this way instead, but it's still a trapezoid. And we want to find the area of this trapezoid. I want the area of this trapezoid. So the area of a rectangle is just base times height. The area of a trapezoid is average base times height. So what do we mean by average base? Well, a trapezoid has 2 bases. It's got a base 1 and a base 2. And the 2 bases are the parallel sides. Those form the 2 bases. So if you're confused about which sides are the bases, they're the ones that are parallel. So for us, this is B1 here, and this is B2. Those are the parallel sides. And the first base has a length of f of 1. And the second base has a length of f of 3. So we want the average base, so that means add them together and divide by 2. So area equals f of 1 plus f of 3 divided by 2. That's the average base right there, times the height of the trapezoid. So the height of the trapezoid is here, and in our trapezoid, it's just right here, the height. And since ours is turned on its side, that means the height of our trapezoid is that distance right there, and we know that that's 2. So I'm going to multiply by 2. Again, let me just write out the formula for the area of a trapezoid. It's the average base. So you can either say B1 plus B2 divided by 2, or you could say 1/2 times B1 plus B2 times the height. Average base times the height. Our next trapezoid, the subinterval goes from 3 to 5, so we follow 3 up, then we follow 5 up till we hit the curve, and we connect those 2 points, and that's our trapezoid there. So the area this time, half of f of 3 plus f of 5, and then times the height, which is 2. And then the last subinterval goes from 5 to 7, so we follow that up, and then we get our trapezoid here. So overall, let's go ahead and write this out this time. So it's 1/2 f of 1, f of 1 plus f of 3 times 2 plus 1/2 f of 3 plus f of 5 times 2 plus 1/2, and then this one is f of 7, so f of 5 plus f of 7 times 2. Now, in this case, it works out kind of nicely because the 1/2 times 2 gives us just 1. That won't always be the case that the width is 2. So the 1/2 won't always cancel out so nicely. But each one of these terms is being multiplied by 1/2. So we could factor out the 1/2. And each one of these terms is being multiplied by 2. So we could factor that out as well, giving me, if I factor that out, the 1/2 times the 2. And obviously, we would probably just write that as the number 1 and then not even need to write it at all. But if it wasn't a 2 there, if it was some other number, then we could factor that out and keep it on the outside. So then all we would have left, notice, I'm going to write it out this time, f of 1 plus f of 3 plus f of 3 plus f of 5 plus f of 5 plus f of 7. So we've got some repeats in there, right? The f of 3's are repeated, the f of 5's are repeated. And that's because this base right here is being used in 2 of the trapezoids. It's being used in the trapezoid to its left and in the trapezoid to its right. So sometimes you'll see a shortcut for this rule where you know each of the interior points here are going to get used twice, and the one on the far left and the one on the far right are only going to be used once because they're not being used for 2 trapezoids. They're just being used for the first and the last trapezoid. Okay, so we can, sometimes you'll see this formula as 1/2 times and then whatever the height is, and then you'll have your like f of 1 plus 2 times f of 3 plus 2 times f of 5 plus, and then your last one, f of 7. And then, of course, the f of 1, f of 3, f of 5, f of 7, those numbers can change as well depending on your subintervals, how wide they are, and how many of them you have. Okay, so let's look at that approximation. We're getting 38.667. Now, the interesting thing here is that each one of these trapezoids underestimates the actual area. It's not like the left Riemann sum or the right Riemann sum where some of the rectangles were under and some of them were over, or the midpoint Riemann sum where each rectangle was a little bit under and a little bit over. Here, every single trapezoid is under. And that has to do, obviously, then not with whether the function is increasing or decreasing, because when the function is increasing over here, we're under, and when the function is decreasing over here, we're still under. So increasing, decreasing has nothing to do with it, but what is going to determine that is the concavity. It's because this function is concave down that each trapezoid is giving us an under approximation. If the function were concave up, and you were creating trapezoids on given intervals, it's going to be a little bit hard to see here. But your, I exaggerated that a little bit, but your trapezoids, you'll see in this case, are each going to be over. So it has to do with the concavity. If your function is concave down, the trapezoid sum is going to be an under approximation. And if it's concave up, your trapezoid method is going to give you an over approximation. Now we can do better, again, by shrinking the width of the interval. So if we use intervals of width 1, then you can see there's very little difference between the actual area and the estimated area. We're getting really close to approximating the actual area under the curve there. And what if we made these trapezoids have an even smaller width? I say width, so I'm kind of interchanging the words width and height here. But the subintervals, let me say it that way. If we make each of these subintervals smaller, then our trapezoids are going to do a better and better and better job at approximating the actual area. So here was our best midpoint sum. Actually, I don't think it was our best. We did one where the width was 0.5, but we didn't see a trapezoid where the width was 0.5. So comparing the two where we did use equal widths here, which one do you think is better? Well, it's kind of hard to tell visually, again, because with the midpoint sum, you've got each rectangle a little over, a little under, and they seem to be balancing well. So that should give us a good approximation, 40.167. But the trapezoid sum also looks really good, although we can tell that it's still under. The actual area is going to be more than 39.667 because our trapezoidal approximation is completely an underestimate. Each one of those trapezoids is an underestimate. So the real answer is a little bit more than 39.667, but we're not sure how much. It may be better than the midpoint technique. It may not. It's hard to say. But these are two really good techniques. These are both better than a left Riemann sum or a right Riemann sum, unless we can find a way with our left Riemann sum or right Riemann sum to make those intervals incredibly tiny in width. Let's practice some approximations. So in these problems, we are given a lot of information, more than you would normally be given in a problem. We are given the equation of the function f, we're given table values for the function f, and we're given a graph. So typically you wouldn't know all of that, but this is just here to connect our thinking. We can verify our results visually, and it just helps us understand algebraically what we're doing or numerically what we're doing. So we want to approximate the area under the function f of x on the interval from 0 to 5. And we have some table values that are going to help us out here. We're going to use the left Riemann sum and 5 equal sub-intervals. So the width of each of your sub-intervals has to be the same. And that means we're going to go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. That gives us 5 sub-intervals. And I like to actually draw above my table. Let's get a little visual representation here of rectangles. And of course, the actual rectangles don't all have the same height. Again, this isn't supposed to graphically match what's happening. It's just a visual to help me organize my thinking. So I know I'm setting up rectangles. They each have a width of 1. So I like to write the width of the rectangle above where I drew the little rectangles. And then for the height of the rectangle, we have to check which method we're using. So here we're using a left Riemann sum. For that first subinterval from 0 to 1, we're going to use the left endpoint. So I'm looking at the 0 right here. We're using that to determine the height of the rectangle, and that's determined by the value of the function at x equals 0, which is 2. Okay, so the height of that is going to be 2. And then for the next subinterval, it goes from 1 to 2. We use the left side, which is 1. That function value is 3. So that rectangle has a height of 3. The next one has a height of 6, then 11, and then 18. We never actually use the last function value when we're doing a left Riemann sum. We start with the first one. We don't need to use the last one. Then to get the area of each rectangle, we just multiply the widths and the heights. So the area is approximately, and remember this is just an approximation. It's not going to give us the exact area, so we should be using an approximation symbol. The area is approximately, and then we just go through and we multiply width times height for each rectangle and add them up. So 1 times 2 plus 1 times 3, and of course you can do this in your head. You don't have to write this out. Plus 1, but I'm just showing the setup to make it super clear what we are doing here to get that approximation. And then we would just simplify that to get our estimate. Does this give us an over or under estimate? So it's nice having the graph there as a visual reference. We can see right away that we're getting an underestimate because the rectangles do not capture all of the area under the curve. If you don't have the graph to look at, then you can still observe in the table that f of x is increasing. And remember what we said, it doesn't matter if it's increasing concave up, concave down, or linear, so you can just do a sketch. It's okay if the graph actually looks like this and you sketched it like this, it's fine. You just need increasing behavior. And once you get a little increasing graph, then draw one left rectangle and you can see easily that it's an underestimate because the actual area we're trying to get is under the curve like that. And so we're not capturing it all. It is an underestimate. Next example, we're going to use a right Riemann sum and 5 equal subintervals to approximate the area under f on the interval from 0 to 5. So again, I would just do my 5 subintervals, just making little rectangles, not to scale, of course, and then the width is 1. And then the heights this time are determined by the right endpoint of each subinterval. So for the first subinterval, it goes from 0 to 1. We use the right endpoint 1, and that's going to determine the height of the rectangle. So we don't actually use the first function value at our left endpoint of our first subinterval. Not when you're using a right Riemann sum. You use the right. So 3, and then for this next one, it's the 6. For the next one, it's 11. For the next one, it's the 18. And for the last one, it's the 27. So this time it's going to be 1 times 3 plus 1 times 6 plus 1 times 11 plus 1 times 18 plus 1 times 27. And visually we can see that we have an overestimate this time. Increasing function, right Riemann sum, is giving us an overestimate. Let's try this again using a midpoint Riemann sum and 5 equal subintervals. So this is more challenging because the height of each rectangle is determined at the midpoint of the subinterval. So not at 0, not at 1, but halfway between at 0.5. The width of each one of these is still 1, so that makes it a little bit easier. But we have to determine the height of the function at 0.5. We cannot get that information from the table. It is not safe to assume that it is halfway between these two values because we don't know. There could be a spike on the graph in between 0 and 1. So it really could be, even though it goes from 2 at one endpoint and 3 at the other, halfway in between, it could be at 1,000. We just don't know. So we're going to use the function to help us out. We would have to calculate f of 0.5 or f of 1/2. So f of 1/2 equals 1/2 squared plus 2. And we would have to go through and do that at 1.5, 2.5, 3.5, 4.5. Okay, then we're going to multiply each of those heights by the width, which is 1, add them all together, and we're going to get 51.25. We don't know if this is an over or an underestimate when we're using a Riemann sum, unless you want to have a really accurate graph and then you can check each one. It could be that you can tell, but I think it's going to be really difficult to tell, you know, even as we're getting towards the end here where the curve isn't quite as curvy. It's really hard to tell which one of these little shaded parts has more area. So it's hard to say with this one if it's going to end up being an overestimate or an underestimate. Okay, and then a trapezoidal sum with 5 equal subintervals. So for the trapezoidal sum, you can still just draw rectangles as reference. I like to draw them to kind of look like trapezoids. So I will just put my dividers there with this 1, 2, 3, 4, 5, and then I just make them go up like that, just to remind myself that they are trapezoids. But again, it's not, this again just there to help me organize my thinking. It's not to scale. So the width here is 1. So I would go ahead and indicate, and it doesn't always have to have the same width, especially when you're given a table to work with. You just have to go with whatever's given to you. They don't have to necessarily all have the same width. It's nicer when they do because it makes the calculation a little easier. Then remember with the trapezoidal sum, we need to multiply these heights, which are all just 1, by the average base. So to get the average base, you're averaging the left function value and the right function value for each subinterval. Look at those endpoints. The first subinterval goes from 0 to 1. So look at the function value when x is 0. When x is 1, we're going to average them. So 2 plus 3 is 5 divided by 2. Then we're going to go over to the next one. We're going to average the 3 and the 6. 3 plus 6 is 9, and then divide that by 2. Then take the next 2. So 6 plus 11 is 17. It's going to be 17 over 2. 11 and 18 is 29 over 2. We're averaging them. And then the 18 and the 27 is 45 over 2. So average base, I already took care of those. That's the number I wrote on the inside. You multiply the average base times the height. So 1 times 5 over 2 plus 1 times 9 over 2 plus 1 times 17 over 2 and so on. Then we add those all up. And we get 52.5. Because the function is concave up, we know that this is an overestimate. Now looking at the graph visually, we can see, yes, it's an overestimate, but not by that much. Like this does a pretty good job of approximating the actual area. Now, in all of the examples we looked at, we were in quadrant 1, where x is positive and y is positive, and we didn't see any rectangles that were below the x-axis. So this is just here to show you some of the different things that can happen depending on the behavior of your function. If the function is above the x-axis, then things look pretty normal. Those are the examples that we've looked at so far. If your function value crosses the x-axis, so at an x-intercept, if that's the point you're using to determine the height of your rectangle, which is what's happening right here, then the height of the rectangle is 0. So the area of the rectangle is 0. It just looks like there's not a rectangle there at all. Technically, there's not, right? Because it just has an area of 0. So that can happen as well. But then if we have a portion of the graph that's below the x-axis, let's say this was our subinterval, -4 to -3, and we're using a left Riemann sum. So at -4, when x is -4, we follow that to the function, getting this point right here, and that determines the height. So the height of our rectangle is down below the x-axis. And so we just go across using that and creating this rectangle. So sometimes the rectangles are below the x-axis and sometimes they're above, which is why, it's technically not true to always call this the area under the curve. Sometimes it's the area above the curve, sometimes it's below the curve. It really just means in between the curve and the x-axis, the area in between the curve and the x-axis. So this is what, this looks like for a left Riemann sum for this particular function. Here's what a right Riemann sum would look like. A midpoint Riemann sum. A trapezoidal sum. Now this trapezoidal sum is pretty good. This is pretty good because finally we have the exact area that we are trying to approximate. So again, when we say area under the curve, here you can see it's not always literally under the curve. So this area right here is above the curve technically, but we still call it the area under the curve. But we really just mean the area between the curve and the x-axis. So now we're going to make a connection between the area under the curve and the definite integral, which we talked about in our last lesson. Use the table of values to approximate the integral of f of x dx from 0 to 25. So we haven't seen this notation before. We're going to talk in detail about where this notation comes from in the second part of this lesson. So for now, just know that this is representing the area under the curve. So I'm going to actually call the curve f of x, right? It's the area under f of x, and I'm going to put under in quotes. It's the area under f of x on the interval 0 to 25. So if you're asked to approximate this integral using a midpoint sum, 3 subintervals, that means we have to take the interval from 0 to 25 and split it into 3 subintervals. Now, because we're working from a table, we can't force all 3 intervals to have the same width. If you were working with an equation, then yes, we could, split that distance of 25 into 3 equal parts, and each interval would have the same width. But in the table problem, it's not always possible to do that. So you just use what you have. You're starting at 0. We can go from 0 to 7 as one subinterval, and then 7 to 15 as our next subinterval, and then 15 to 25 as our last subinterval. Then from 0 to 7, that has a width of 7. From 7 to 15, that has a width of 8. And then from 15 to 25, that has a width of 10. Now, we're supposed to use a midpoint sum. And so if the interval starts at 0 and ends at 7, the midpoint of that interval would be 3.5. And thankfully, we have that value shown to us in the table, 3.5. So the midpoint value of the function is f of 3.5, or 6. That's what we're going to use for the height of our first rectangle. On the interval from 7 to 15, you go to the middle. The midpoint between 7 and 15 is 11, and use that function value. Now, it's -10 because it's below the x-axis. We keep the negative sign there. And then on the interval from 15 to 25, halfway between is 20, so we take the function value at x equals 20 to be the height of that rectangle. To get the area of each rectangle, you multiply the width and the height. Okay, so the area is approximately 6 times 7 plus 8 times -10 plus 10 times 8. And that is that's the approximation for this integral here. We're not going to use an equal sign. It's just approximately. 42 plus, oh, that's easy because that's -80 and that's plus 80. So it's just going to be 42 for our answer. It's okay that the area calculated here is a negative number. typically area can't be negative. It doesn't make sense conceptually to say the area is negative. But what we're going to see is that when we have this shaded area below the x-axis, we represent it as negative 1 times the area. So we call it signed area, right? This is going to have a negative area. This is going to have a positive area. This is going to have a negative area. When I say negative area, I just mean negative 1 times the area that we've shaded there. Thanks for joining. I'll see you next time.